So this is the 13th week of CS204. Today we are going to see new topics, namely threads and processes and mutexes. We are doing the video lectures, video recitations online because of the pandemic. And let's start then. I'm sharing the screen. If you have questions, you can use your mic or you can use chat. Okay, so in our computer, very often we, at the same time, simultaneously, we run multiple programs, okay? And those programs that are being currently executed in your computer, on your machine, are called processes, okay? So a program that is being currently executed is called a process. If you want to see the processes, you can just press Control Alt Delete. And here we go with the full list of processes. And actually, these are the processes that I've been generating. So Microsoft Visual Studio, Zoom Meeting, Paint. If I want to start a new process, then let me start with Notepad, let's say. You see, I didn't have previously a Notepad, but now I have it here. It's a new process. It's a new program being run, okay? If I close Notepad, you'll see here I don't have it anymore. And if you see the full list of processes that I'm using, it's here, okay? And there are dozens, maybe even close to 100 processes. And the problem is that my machine is, for simplicity, let's assume that it's single core and I have one processor. Having one processor means that at a certain time I can only execute one program, okay? But as you see, I have many programs. So why it is the case? Well, the reason behind it is because what I do is that in pseudo-parallel manner, pseudo-parallel way, I'm executing multiple programs, I'm working on multiple processes at the same time. I do it in a way that I give to one program a certain amount of the processor, then to the other one a certain amount of time of the processor, to the other one a certain amount of the processing power, etc. Then I switch back to the first one, second one, third one, fourth one, etc. As you can see here, Zoom, let's say, it's wasting like 35% of my processing power. Then this is, so most of those processes that you see now are generated from the operating system, okay? Because I generated only maybe like not more than 10 processes, but the other 70, 80 or whatever are generated from the operating system, from Windows, okay? And you see how much processing power they use, okay? You see it here, okay? So this one is using 3.6%, this one is using 4.6, and this one is using 9, and system 14, etc. And not only processing power, they use memory and hard disk and network resources, etc. Okay, so here you can see the full list of processes which are being executed in a parallel or actually pseudo-parallel manner. This is from the task manager. I'm going to delete it. So basically, this is what happens. This is the time that processes spent in my computer. Roughly, I mean, this is just to show you, because some processes take more time, the others take less time, depending on the needs of the processes. So let's say this might be your Microsoft Visual Studio code that you're writing on. This might be your game that you're playing on the same time. This process might be, I don't know, maybe Microsoft Word that you're typing on. This might be an audio file that you're listening or whatever, maybe a movie at the same time. So part of that you give to one process, another process, another process, another process. Then when you're done with that, again, you switch to the first one, which was Microsoft Visual Studio. Then was this game or Microsoft Word or audio file that you're listening or video file that you're watching or maybe YouTube video, whatever. Okay, so now that's why you see that you have an impression that you're doing in parallel all of them, but actually it's not the case. What you're doing, you're in pseudo-parallel way, one at a time, you are executing them using your processor, of course. That's why when you are using really a lot of processes that demand a lot of processing power, you see that your screen freezes. Okay, maybe our senses are okay if you are using like 2 or 3, depending on your processor power. If you're using 2 or 3 processes or programs that are being executed, maybe you can not feel when it's freezing, okay, because our senses are not enough to feel it. But when you use a lot of processes, then those processes don't get enough of processing power, then our senses, eyes and brain can see that actually, you know, they don't get enough of processing power because the game is freezing, or the video is freezing, or the audio is freezing, etc. Okay, so we saw what the processes are. They are programs that are being executed right now, as simple as that. Now, we saw that we are executing multiple programs. Why do we do that? For efficiency, okay? Because as you can see, I mean, right now I'm executing multiple programs, not only Zoom, but others, and still I cannot sense it that I have a feeling that I'm using multiple processors for them, although I'm using one processor. Let's assume that it's one core processor, because multiple cores is like having of multiple processors in one chip. But it's something advanced. It's not related to this course. It's about computer architecture and microprocessor systems. So I'm doing this for efficiency reasons, because not all of the programs need a lot of processing power. They need a small amount of it. So that's why if I give portion to one, to another, to another, to another, I can basically feel like I'm doing executing multiple programs. So I have multiple processes in my computer. What's interesting is that those processes kind of, in quotation mark, fight for the processing power. Okay, they want to grab as much time as they can from the processor. But of course, the operating system doesn't allow the processes usually to determine how much time they need. Usually determines with kind of analysis and kind of communication with the processes, how much time each process, each program, each process needs. This is another advanced topic. You're going to see it in more details when you take the operating system course and the scheduler and processes, how they are scheduled, etc. So what I wanted to tell you that this is actually processes are kind of like companies that they see other companies as concurrency. You know, they want to grab as much market, as much people as they can from the other companies. And processes in similar fashion want to grab as much processing power from the others, okay? However, very often, this is what happens. You might run what is called, let's call them lightweight processes that work towards the same goal. For instance, you're using Microsoft Word. Okay, you're using this text editor and you're writing a text. And in this Microsoft Word, in the same environment, in the same document, you need maybe multiple functions, or let's call them for the time being processes, to do your job. So one of them would be the following. When you type something, you want to find the English typos in English language, grammar mistakes maybe. And whenever there is a mistake, you see those red lines, okay, or maybe blue or green lines when there is, you know, some grammar mistake. And when there is a typo or misspelling mistake, you see those red underlines, etc. This is one process, okay, then one function, okay. Another one might be the following. While you're typing, there is kind of a while loop, if I can say so, that is waiting for your input, and then it immediately wants to display your input on the screen. Okay, this is another process. Let's call it lightweight process. Another process might be the following. Let's assume your Microsoft Word document has hundreds of pages, maybe 1,000 pages. What if somewhere on the 5th page you make a change? Okay, you delete a table or you add an extra picture, whatever. Well, if you do that, maybe all of subsequent paragraphs, tables, or most of subsequent paragraphs, tables, images, objects, or whatever in your document should change their page, and should change their page to which they belong. Maybe what was something in the 6th page, now it's in the 7th page. If something was in the 10th page, maybe now it's in the 11th page, etc. So you make only one change, maybe in the 5th page, but you make a lot of other rearrangements in the subsequent page up until you go to the 1000th page, maybe. Okay. So when you make these kind of changes, there's another process, another function, let's call it, that it's madly doing some computation to figure out which photo, which figure, which table, which paragraph belongs to which page. Okay, so as you see, those 3 processes, the one that is checking the grammar errors and typos, and the one that is taking user input and printing it on the screen, and the one that is doing those math computations when you delete something or add a new object, picture, table, whatever. All of those work towards one goal: to make your Microsoft Word experience as better as possible. Okay, and those 3 lightweight processes shouldn't see each other as enemies, as concurrency. Rather, they should cooperate with each other. Well, those programs or those functions, if you will, or sometimes they are called lightweight processes, are called threads. So if multiple functions work towards the same goal, they share the same environment, same document, same variables maybe, etc., then they are called threads. Okay, so this is how we represent processes with circles, and each process now might have multiple threads. You can assume threads are kind of functions that works toward the same goal. So if this is your Microsoft Word document, then this might be maybe the grammar spelling the error check and grammar spelling function that finds your mistakes. This might be, so threads are like kind or represented with this curly line. So this might be, okay, so this is your grammar checking function. This might be maybe your function that is waiting for user input to, and that the user gives from the keyboard so it can print it on the screen. And this is maybe your editing function. Okay, if you make a change, it just computes which one is to which object, which paragraph, picture, table, whatever belongs to which page when you make some changes on, when you add or delete some objects. So those threads work towards the same goal, and that old goal is called the process. Maybe it's called Microsoft Word. Okay, you might have another program that has now, so Microsoft Word maybe has 3 threads, but another one has 5 threads, etc. So multiple threads, which are functions that works toward the same goal, form a process. Okay, and you might have multiple processes. So assume those are like, you know, processes are, as I told you, companies, okay, that they see each other as concurrency, want to grab as much time as they can from each other. And those companies have workers, which are those threads. And threads of one company, of one process, see the threads of the other company as concurrency. They want to take processing power from them. However, threads inside of a process, just like workers of the same company, they try to cooperate with each other. They don't see each other as concurrency, rather they cooperate with each other. In that sense, so while processes try to grab as much time as they can from each other, threads that are inside of the same process actually cooperate in this sense. So what is more important, to see the grammar checks, or maybe if you type your text, you want to see it displayed immediately? Well, of course, the function or the thread that takes your inputs and prints it on the screen is more important than grammar check. Maybe you can do the grammar check later on after 5 seconds. But you don't want to see your output after 10 seconds. You write it and wait 10 seconds and you see it. You want to see it immediately. Okay, so maybe the thread that is taking your input and printing it into the screen is the more important thread. That's why it should have priority. It should be executed first, when it should be executed. Maybe the second one should be the grammar check, because you don't want to see the grammar checks after 1 minute. You want to see it maybe after 5, 10 seconds or so. And the third priority, maybe it might be given to the thread, to the function, that when you make a change in a certain page, when you delete or add a new object, picture, table, paragraph, whatever, you want to rearrange things and see which paragraph, which picture, which table belongs to which page. Well, maybe it's not important to see it immediately. Maybe you can see it after 30 seconds, after 1 minute maybe, okay? But you want to see your text immediately displayed as you type it. That's why threads inside of a process, they cooperate with each other, okay? They don't want to grab the processing time, okay? They just want to make the working environment as pleasant, as comfortable for the user as possible, okay? So now we know what are processes, which are programs being run, and we know what are threads, okay, which are also, we call them lightweight processes, but sometimes multiple threads work for the same process. And one process at least should have one thread, okay? And processes have the thread, which is the program that is being executed, and besides that, they have the local environment, which are variables and other stuff. So we are not going to get into details about those topics because they're not related entirely to CS204. You should see them in details when you take the operating system courses I said. Now, we saw what threads are now. And let's see how we can implement threads in CS204. Well, for this reason, we have something, a class actually, and the name of the class is called, as you might guess it, threads, okay? And let me see what is inside. Let's write what's inside of the class. We are going to write only the most important public functions of the class thread, and they are the following. Of course, the constructor, and we are going, the parametric one, we are going to see it later on again. Then there is a function called getID. All of the threads have its own ID that is given by the operating system. Then join, which is very important. This is when you want a certain thread to wait for the others to finish. They are joined towards a common goal and wait for each other. Detach, when a process is working, a thread is working for one process, sometimes you just, and so basically see threads like workers in a company. Sometimes you give one job to a worker, and when the worker is finished, then you might give another job to the same worker, okay? So when you give him one job, okay, you join it with one group of workers or whatever. But when it's finished, you can detach it and give another job to the same worker, okay? Instead of firing that worker and renting or hiring another worker, you can use the same worker, okay? The same goes for threads, okay? Because deleting a thread, creating new takes some time. It's not too much, but takes some time. That's why you don't want to delete it. You just want to assign a new job, to a new thing to do, a new function to do to that thread, okay? That's why there is the detach function. When you want to them detached from other threads, then there is a function which is called sleep for. Okay, sometimes you want a thread to sleep for a certain amount of time, not do anything. Okay, it's like saying to a worker, okay, you can take a break for like 2 hours and I give you another job. And here you don't give 2 hours of sleeping, of course, you give a few milliseconds usually, to maybe at most hundreds of milliseconds or so. Then, since the threads don't compete for the processing power, they cooperate with each other, threads in the same process. There's a function which is called yield. That means since one thread can be executed at a time, sometimes one thread might voluntarily give its processing time to another thread, which is more important. You remember the Microsoft Word example. Maybe the grammar check might yield its processing power to the grammar check thread. The grammar check function might give its processing power to the user, to the thread that is taking user input and printing its input into the screen when the user is typing a lot. Okay. So is that something else to do? No. Now let's see how a thread can be initialized. Well, for that sense, let's see a certain function. So this is function. Function 1, maybe. Let's call it like so. Function 1 has some parameters, like parameter 1, parameter 2. Of course, you have like integer, power, or float, or double, whatever. And parameter n. Now, usually, roughly, threads threads are assigned a function that they should execute. And how do you do that? Well, this is how you do it. We saw the function. So let's now write a thread that its job is to execute this function. Okay, and there might be multiple functions in the same project, in the same process, and each function is basically assigned to a thread, and all of those threads form the process. Okay, so thread, let's call it my thread, the name of the thread. So this is the type name, data type, which is thread. I'm creating an object called my thread, and this is the constructor. The first parameter of the constructor is the function name. Okay, so it's now called, the function name is function 1, so I give function 1. Then I give the parameters that the function is taking, parameter 1, parameter 2, up until parameter n. Here in the beginning, I put an ampersand, and you can see on it as kind of a reference. Basically, this ampersand is saying, so the function, when you write it, it's in the memory, and it has a starting address. Okay, and ampersand, whenever you see it in C++, it means an address. And it's not necessary to be an address of a variable, okay? It can be an address of a function also. Basically, with this stuff, I'm telling my thread that you should start executing a function whose address starts from here, okay? If you don't use it, it's not a mistake, but I prefer to use it. Because if you don't use it, you kind of make a copy of the function, okay? But if you put it ampersand, you don't change the function, you just use the same function, which you have already written. Anyway, so let's see an example about this. Today we're going to see 4 examples. This one. Those are the examples. So let's start with which one? We are going to see first the independent threads. Let's see how threads work then. So this is my thread. Okay. This is my function basically, and my program. I have a global variable called maximum 7. And I have a function called function 1. It takes only one integer, which is the ID that we give to the thread. And in a for loop, which iterates for 7 times from 0 up until maximum, this is what I do. I use a variable of type ostring stream. It's called output. In that ostring stream, I just say thread with ID, which is the ID that I gave it to him, 1 or 2, because I'm going to use 2 threads in this program. And then I'm using, this is how you get this thread, get ID. Okay, so this is the ID that the operating system gives to the thread. Okay, and you remember this pointer when we were dealing with classes, when we were defining classes. Well, in similar fashion, you have this thread. Okay, so from the thread that is now executing the function 1, I'm taking the ID and printing it. And it's working with I is equal to, I goes from 0 to maximum. After that, I put this output, ostring stream, convert it to string, and print it to cout. This is it. Now let's go to main. In main, we declare 2 threads, thread 1 and thread 2. And here you go. I give first the function name that I'm going to execute, is function 1, and then I give the parameters that the function takes. It takes an ID, integer, so I give 1. Thread to similar function is going to execute function 1 again. Now this is just to show you how threads work, how we initialize threads, and it has integer ID too. By the way, this is important to know because you might get tricky questions in your exam. Main is also a thread. So main is a function, and there is a thread which executes main. Okay, so at least you have one thread in your program when you start to run it. But now, besides the main, I have 2 other threads, which are thread 1 and thread 2. And afterwards, I join them. I join them to the main thread. What does that mean? That means that main cannot finish without thread 1 and thread 2 finishing. Because if main finishes, when it's going to return 0, the program is going to finish. Okay, and it's going to basically terminate. When the program terminates, even though if those threads, thread 1, thread 2, didn't then finish their job of executing function 1, yet they are going to be finished. Okay, they are going to be terminated by force. And we don't want that to happen. What we want thread 1 and thread 2 to finish their job by executing function 1, and then we want main to finish. Okay, that's why we join them. Okay, kind of, they wait for each other, cooperate with each other towards a common goal. Okay. Because it's like this. Now, if you want to join, nice question. Because here, if I say only this thread join, okay. If I say this thread join, I'm actually accessing main. Okay, because this thread means that the thread that is currently executing the main function, it's the main thread. Okay, but if I want inside of the main to join other threads, I have to use it this way. However, if you see function 1 is going to be executed twice by 2 threads. So I cannot say here thread 1 or thread 2 because function 1 actually doesn't see neither thread 1 nor thread 2. But inside of them, the thread that is executing function 1 can see itself, of course. That's why I'm accessing them by using the get ID of that particular thread. Now this ID is going to be the ID of thread 1 and sometimes the thread 2, depending on in which thread we call this get ID. Let me run the function and it will be more clear, I suppose. Okay. So I'm running the function now. Let's see the output of the function. Okay. Okay, so this is your output. This is thread 1. And thread ID that the operating system gave to the thread is 10,104. It's working with I0, then thread 2, thread 1, thread 2, etc. Okay, this is how it works. If I run it again, I'll get different IDs for the threads. Okay, this is my output now. It's not necessary to get it in a tidy way as you see it, okay? You might get it in different way. Anyway, so thread ID, whenever it's called inside of the thread 1, it gives the ID of thread 1. Otherwise, it gives the ID of thread 2. This is what happens. Okay, now, since we have the limitation of 40 minutes, and I'm also recording the videos, which might be shared with you, let's stop over here and please re-log in again. So, because I'm going to tell you some stuff related to some problems that we're going to see with threads right now. So I'm stopping now and we can immediately start. Okay, immediately re-log in again. Okay, now let's go back to the code. And let's see some problems that we might encounter with the code. So, what happens basically here is the following. Let me draw it to you. Should I leave it here? Okay, maybe I should leave it. Maybe I should start a new paint. So what happened previously is the following. Okay, so I have a function. Inside of the function, I had the output, which was OString. So this is my output, which was OString string. Okay, output. And this was done by thread 1. In similar fashion, I had also thread 2. Basically, they're running the same function and instances of the function. Okay, so you see that this output over here is actually kind of a local variable. And what happens is the following. You don't see it, but this is how it works. And we have the cout. And cout is kind of a function, or if you wanted, class object that is shared among all of the objects and functions of the program. Everyone can see cout. But output is kind of local for threads. Now, when thread 1 starts executing, basically this is what it's doing initially. It says, okay, thread 1 has, and it stops now. The program might stop it at any time. Okay, now it says, because you're doing them in pseudo-parallel manner, it might say to the thread, okay, you finish your job. Now it's time for thread 2 to continue. And then thread 2 is doing the same thing. So what they're printing, so thread ID, blah, blah, blah. So thread 2 has thread ID. And just when it's about to continue, it stops. Now it's time for thread 1 to continue. It continues where it's left. Has thread ID, which is 1954 maybe. This is a random number. And it stops. Now it's time for thread 2 to continue, etc. Whenever this job is finished with the output, and I then go and print it to cout. Now, you might say, why do I complicate my stuff? Why I don't immediately print it to cout? Nice, let's do it. So I'm commenting out OString stream and cout. By the way, in order to use OString stream, you should include SS stream. So instead of output, I directly print this to cout. Okay. Maybe we should just remind ourselves. So this was the output when I used local variable OString stream. That's it. Let's not forget it. Let's keep it actually. So I still have it. It's here. Now let's do the changes that I told you. Instead of using local variable, let's directly print them to cout. And you see cout is kind of local for kind of global for all of them. All of them can see it. And also remember that with threads or processes, you never know when the operating system is going to stop you. Okay, it can stop you at any place it wants. Okay, that's why you get always an input, an output that is, you know, weird, looking random, etc. So let's run the code now. Remember this tidy code, now output. When we get local variables, now let's see what is going to happen right now. Well, this is what we got. This looks untidy. Kind of like the outputs of the threads are scrambled, okay, garbled with each other, mixed up. So why is it happening? Well, it's because now they share cout. And when they share cout, maybe it's not time for thread 1 to start. And when thread 1 wants to print has thread blah blah, its input, output, which is this one, it is stopped and says, and the compiler says it's now for the other thread to continue. So now thread 2 starts. Remember, now thread 1 has stopped here, so it should continue with an empty space. 1 has thread ID, blah, 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 with this part over here, basically. And now it's thread 2 continuing. Has thread, and it's stopped now. Now it's time for thread 1 to continue. And it starts 1 has thread ID 1954. Okay. And then now it's time for thread 2 to continue. And it was stopped at ID. So this is what happens. Whenever you see a semicolon, that is going to be printed. That's why this is the output you get. Okay. So on one side, we want to have parallelism or pseudo-parallelism for the reasons you saw it. Okay. Sometimes some programs are waiting for input, and while the user is giving his input from the keyboard, maybe, and it's for you, it looks a small amount of time, maybe seconds. But seconds in terms of processing power is a lot, because in terms of seconds, you can finish a lot of jobs in your computer. That's why I want to have parallelism. But when you have, or pseudo-parallelism, okay, parallelism, real parallelism happens when you have multiple processors. But when you have only one processor, it's pseudo-parallelism, because threads or processes take turns in executing themselves. But when you have parallelism, you might have problems like this one. So it doesn't look consistent. I'm going to tell you another problem. And so this was one problem. I'll tell you another problem, and I'm going to show you the solution of that problem also. So let me go then with an example that you see maybe on Sabancı University campus. So, or maybe I should show this photo over here. Assume you're in Sabancı University campus. At the campus, you might upload your printouts, your documents or whatever. And let's assume that when you upload them, immediately they're going to be printed. But first, and there's only one printer, let's assume it. And the printer is basically, when you upload them to a queue. And queue, you remember queues, they work in first come, first served order. Now, since there are thousands of students and maybe hundreds of TAs and instructors and LAs in Sabancı, we cannot have separate queue for all of them. What we do is the following. We have one queue for all of the Sabancı students, professors, LAs, TAs, or whatever. And when you upload something to the queue, in the commonly shared queue, you are going to use a program. Okay. Now, when you run that program, that becomes a process. So let's assume that this is the spooler directory, which is basically the queue where we print the document, we keep the documents that we want to print, and they are printed in first come, first served order. So we have used 6 slots. Maybe we can keep here a variable which we might call as empty slot, maybe, which keeps the next empty slot. Okay, and the next empty slot is, as you can see, 7. So the next empty slot is 7. Now your program, and you have 2 processes, or let's say students A and B, at the same time, they want to upload their documents. And since you want your computers to be fast or work on multiple tasks, deal with pseudo-parallelism, you let them run in parallel. Now let's see how might a process or a function look like. I'm going to write pseudocodes, and you are going to see what pseudocodes are. Basically, with pseudocodes, you just give the general idea of what the code is doing, but not the actual codes in C or C++ or Java or Python or whatever. So The code to upload, or the function is very simple. To upload a document to print it might look something like this. So get empty slot. So you see, from 0 up until 7, they are all filled up. The next empty slot is 7. So get that empty slot. It is kind of a comment. Put data to empty slot. Okay. And this is to put your data at the empty slot. Maybe it should be PDF document or whatever. And increment empty slot. Why do we do that? Because now the empty slot is not the 7th. It's going to be the 8th one, the next empty slot. Okay, so roughly, very rough, this might be the pseudocode. This is what the function is doing. And this is what actually let me write it. Process A is doing. Okay. As you see, previously we saw function 1, which was run by 2 threads. Well, this is another, maybe you can see not, okay, this is process because they compete for the computing power. So they might, even processes might execute the same function. Okay, so this is now the same thing that the process B is doing, not A now, it's B. Okay. Okay, so this is what those guys are doing. Process A and process B. So far, so good. Okay. And then let me take process A bit upper. We're going to need it there. We'll see why. And now this is my process A. Okay. Now let's see. Let's assume at the same time they start running, and then the compiler gives priority to process A. So process A takes get empty slot. Okay, it takes 7. Let's say the process A wants to print maybe a PDF file. Okay, and let's say maybe process B wants to print a CPP file or document, Microsoft Word document or whatever. Never mind, it's not important. So process A starts, get the empty slot, which is 7. It put data to empty slot, so I'm putting now my PDF, because this is process A running, over here. Okay, and now, just when I want to increment the empty slot and make it 7 over here, right here, in this place, the compiler says, or the operating system says, okay, stop running. It's now time process B to run. Now process B starts running. What does it do? It's again, take an empty slot, but the empty slot is still 7. We couldn't update it over here. So process B takes 7, put data to empty slot, and I'm putting data to 7. But there is already data over there, but I don't care about it. I don't check whether there's data or not. I don't know whether there's data or not. I just put it. And now I put my CPP file of process B. So this guy is putting CPP now. And then I'm incrementing empty slot. It was 7. It's not 7 anymore. It's going to be 8 right now. Okay, and process B finishes. Now the compiler says it's time for process A to start. Now when process A not start, to continue where it left at increment empty slot. And 7 should be 8 now. So again, it deletes this 8, thinking the poor guy that it is still 7, but it's not. And it's writing 8, incrementing it, but incrementing because of this 7. Now they both finished. And they both think that they have uploaded their documents or files that they want to print. However, that's not the case. Only process B managed to print it. And process A will wait in vain for his document to be printed. This is one of the problems that occur when you are dealing with parallelism, okay? And when you're dealing with parallelism or pseudo-parallelism, especially when you share objects, like in this case, you share this cube, okay? And those kind of shared resources, and by resource, I mean processing power, memory, maybe variable Q, as it is the case over here. Those are called the shared resources, which are shared among multiple processes or threads. They are named as, or they are known as critical regions. Okay, and the problem which occurs when we don't get the output, the outcome that we want, or the outcome is going to be determined by, in terms of which process is getting to be executed, which not, is called race conditions, because those two race for the processing power, for the resources, etc. Okay, so the race condition is the output, the problem that we see when multiple threads or processes access in not a logical way the same resource that they share. This is race condition, and critical regions are basically the shared resources among different processes. I think there was a question, so let's address the question. Okay, and as process A put the data, and it put it to the 7th slot, but process B deleted that and put its own data. Okay, this is the problem. So yeah, it put it, but it was overwritten by process B. And that's why we call this race condition, critical regions. Okay, you get those kind of problems. Now, when we see those kind of problems, how are we going to solve it? One way to solve it is the following. Just a moment. Okay, we can solve these problems in the following manner. Only if we can find a mechanism to allow only one process in the shared resources to work, and when that is working in the shared resources, up until it's not finished, we shouldn't allow other processes to work in the same shared resource. Okay, because the race condition appeared because process A and process B were simultaneously working with the spool directory, with these shared resources. But if we let only one of them be in at a given time, only one of them to be inside of the critical region, and the other one is excluded, then we shouldn't have any problem. So what we are going to do basically is the following. Whenever a process enters or starts working in a shared resource like Q or whatever, then it's going, we call it lock it. That means I'm inside and no one can get in. Okay, and for this reason, whenever process A goes inside, it should lock that resource. Okay, and whenever it goes outside, it should unlock the resource. Okay, similarly, in similar fashion, the same goes, I mean, this is the same function actually. So in similar fashion, the same goes for process B. It's going to lock and unlock stuff. Okay. Now, what happens is the following. Again, let's say process A starts. And when A starts, it's locking the spooler directory, which is our queue where we print stuff. I'm getting the empty slot, which is 7. I'm putting my data over there. Oh, I'm sorry. Okay. I'm putting my data over there, which is the PDF. Okay. So process A puts PDF. And the empty slot is 7. Now I want to increment the empty slot and I want to make it 8. Okay. I want to make it 8, but this 8 should be over here. But I cannot do it because right before doing it, the compiler says to me, stop it. So it says to process A. And says it's time for process B to start. And when process B starts, it starts from here. And process B wants to lock this spooler directory. The problem is that it's already locked. And when it's already locked, you cannot lock it again. So basically, process B is waiting now up until it can execute this lock command. And it can be only executed when the spooler directory is unlocked from someone else. Okay? So basically, even if the compiler, even if the operating system gives its time to process B, it's going to waste it by waiting for the lock to be executed. Okay? So it's not going to execute this stuff because right now process A is inside. And now only when the operating system will give its time to process A can unlock this guy, then put A 8 over here. Okay, and unlock it, of course. Or better, it's like this. So I put A to the empty slot. And then I unlock my lock. So I don't have it anymore. Now when it's time for process B to start, that when the operating system gives its time to process B can lock it because it's unlocked now. It doesn't exist. So it's locking it. I'm getting the empty slot, which is 8. I'm putting my data to the empty slot, which is the 8 slot, this one. And I'm putting my CPP over here. I'm incrementing the empty slot, so it should be 9, and it becomes 9. And then I'm unlocking this guy, so maybe another process can enter it. Now they both have their outputs, their prints out, or documents they want to print in the shared spooler directory or queue. Now, if we saw this, the question is how we can implement this lock using programming. Well, for this reason, we have another class which is called Mutex. Okay, and it's a class. There are two important public functions of the class that we are going to use. There are other stuff, but the most important that we are going to use are lock, of course, and unlock. And you should know what they're doing. Now let's see Mutex. We saw threads, how they work. Now let's see mutexes, how they work. In order to use threads, you should include the thread library. And in order to use mutexes, you should include the mutex library. Okay. So this is my mutex library. And now remember this output that we had with cout. and cout was a shared resource. Okay, just like the spooling directory, the printer queue. Okay, and that's why we got this garbled output. Now, what we want to do is the following. Whenever one thread accesses cout, the other shouldn't do it. Because as I told you, cout is kind of shared among all of the others. While output as output O-string stream was a local variable to the corresponding thread, cout is not a local variable. It's global shared resource. That's why what we are going to do is the following. So using mutex, we are going to define here a mutex. Usually they are defined as global variables, usually. So mutex, let me call it my mutex, or whatever the name. Now, when I want to print this guy, my mutex, I want to lock it. That means when one thread is printing, accessing cout, the other one shouldn't do it. Now this thread is going to finish its job. And when it's going to finish its job, it's very important to unlock it. So I'm unlocking it. Okay, now remember this output? Let's see the same output if I run the codes, how it's going to look like. Now when I put mutexes. Okay. Well, this is tidy. This looks similarly like the output that we had when we had those local O-string stream variables, but the issue is that we don't have it now. But we are using mutexes to reach the same goal. Okay. So up until now, you should have clear idea what threads are. Usually threads are executing a function, and what mutexes are, which are variables that enable us to lock a certain shared resource. So when multiple threads or multiple processes share it, we want only one of those at a given time to be working on it. So mutexes enable us to avoid critical race conditions in those critical regions by locking the resource for only one thread to work on it, okay, in order to avoid inconsistencies. Okay, so we covered only one example, but you learned a lot from this example. We are going to see 3 examples in the second class, and what else? I'm going to explain also the homework. So let's take a break of 10 minutes, and we'll be back. Okay, sometimes output is shuffled like thread 1 and sometimes thread 2. You cannot avoid it because you don't have control over which is going to execute first, thread 1 or thread 2, okay? That's why, because the operating system decides which is executing, thread 1 or 2. You don't have any power of it, okay? So let's take a break of 10 minutes, and we will start in 11:50 for the second class. See you in 10 minutes then.